So, hello students, this is the fourth class of electromagnetic theory, and in this class I am going to teach you about the boundary condition of electric field and magnetic field. Okay, that means how the electric field and magnetic field behave across a medium. Okay, so first of all I am going to discuss about the perpendicular component of the electric field and magnetic field. So, in order to do that, I need an interface. Okay, that means a boundary between two medium. So, here as you can see, I have taken two medium, medium 1 and medium 2, and this parallelogram represents the boundary. So, for 3D visualization almost you can look at this. Okay, so this is what, this is medium 1, this is medium 2, this is the boundary. Okay, and here I have considered a Gaussian pillbox. Okay, such that the Gaussian pillbox, that means the Gaussian surface in cylindrical form. Okay, here I have considered the Gaussian pillbox such that the upper half of the cylinder is in medium 1 and the lower half of the cylinder is in medium 2. Okay, and I have considered, since I am going to discuss the perpendicular component here, so I have considered the electric field in this direction, that means in perpendicular direction. Okay, so this is E perpendicular. Okay, so electric field is in okay, let me change the color. Electric field is in this direction. Okay, this is E perpendicular. Okay, for medium 2 this is also E perpendicular. Okay, and it is perpendicular to the surface. Okay, sorry, interface. I hope you know the difference between surface and interface. Okay, and then what I have considered, I have considered the Maxwell equation. Okay, so the Maxwell equation, del dot D equals to rho. I can write it as in integral form. Integration of d dot ds equals to q, right? I can explain it here. As we know from Gauss law, E dot ds equals to q by epsilon, right? And if I am going to take this epsilon towards left, what I can write, epsilon E dot ds. Again, epsilon E is what? Epsilon E is, it is d, right? So integration d dot ds equals to q. Now, on applying this on this Gaussian pillbox, what we have, I can separate this integral into the integration of two different surfaces. Okay, the first one, this ds1. Okay, this is what, this is in upward direction. Okay, this ds1, this is in upward direction, ds1. And then for the lower surface, this is ds2. These two are what? These two are plane surface. Okay, and then the curved surface. Okay, here the curved surface, the direction of the curved surface will be what? ds3. This is in radial direction. Okay, it is radially outward. And now I can write down it as this equation as what? Summation of, that means the sum of these three integration, d dot ds1, one for this surface, d1 ds1 surface, and then for ds2 surface, and then for ds3 surface. Okay, which is equal to q. Now, as you can see, for S1 surface D, again, as you can see, D is what? D is equals to epsilon E. So, if I am taking the normal component, that means perpendicular component of the electric field, and since the electric field, as you can see here, electric field is in this direction, so D will be also in this direction. Okay, so D will be also in this direction. These are perpendicular directions. Okay, so now D and S1. For DS1, this surface D and S1 are what? Parallel. Okay, here is the D and here is the DS1. So they are parallel. So angle between them is 0. So cos 0 is 1. So I have written here D is I am writing it down as B perpendicular 1, because this is the perpendicular component and it is in the medium 1. So I have written it D1 perpendicular. Okay, and then for this term, okay, this term, what I have done for this term, uh, you can consider this situation. Okay, so D is here in this direction and DS2 is in this direction. Okay, and the angle between them is 180 degree. So cos 180 degree is -1. So there will be a negative sign. Okay, so dot product will be D2 perpendicular and DS2, since it is in since the placement electric field is in second medium. So I have written it as D2 and it is perpendicular. So I have written it as D2 perpendicular. Okay, and for D dot DS3, as you can see, what I am considering only the normal component. For normal component, D is in this direction and DS3 is what? DS3 is in this direction. As you can see, it is radially outward and the angle between them is 90 degree. So dot product will be what? Vanished, since cos 90 is 0. Okay, so I can write it down as D perpendicular 1 ds minus D2 perpendicular ds equals to Q. Actually this is Q. If the surface charge density is sigma and the area of the Gaussian pillbox is ds, then the total charge enclosed by the Gaussian pillbox will be what? Sigma dot ds. So this will be total charge. Okay, so I have replaced Q by sigma ds. Okay, and all these three terms contain ds. So I have what? I have removed all the three terms. They will be cancelled out each other. Okay, and then so I can write D perpendicular 1 equals to D2 perpendicular equals to sigma. Again, D can be written as epsilon E, as you can see here. This. Okay, so what I can write? Epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equals to sigma. Okay, so this is the boundary condition for normal component. But now if the surface is charge free, okay, let's say if there are no charge, okay, that means sigma is 0, then what I can write? Then I can write E1, epsilon 1 E1 perpendicular equals to epsilon 2 E2 perpendicular. Because if this is 0, then on taking this term here, I can write it down as this. Okay, so D1 perpendicular equals to D2 perpendicular. So what I can say, the perpendicular component of electric field is continuous when the surface is charge free, or the perpendicular of the displacement electric field is continuous when the surface is charge free. Okay, otherwise this is the behavior. Okay, now for magnetic field, I have considered the same. Okay, this is the medium 1 and this is the medium 2. Similarly, this is the Gaussian pillbox, right? Again, in this direction, it is the magnetic field. Since I am considering only the perpendicular component, so I have written it as B perpendicular. Okay, so in medium 2, this is also B perpendicular. Okay, so as you can see, similar concept. What we know, B dot ds equals to 0 for closed surface, since magnetic monopole does not exist. So I can now separate this integration in terms of these three surface integration, okay, for ds1, ds2, ds3, and similarly using the above arguments as in electric fields, what I can write, B perpendicular ds and B2 perpendicular ds, and this term will be vanished since the angle between B and ds is 90 degree. Okay, and this is equals to 0. So B1 perpendicular and B2 perpendicular are same. So what I can write, the perpendicular component of magnetic field is continuous across the interface. Okay, and as you can see, the surface area of ds1 and ds2 are same. So what I have written, I have replaced this ds1 and ds2 by ds. Okay, since ds1 equals to ds2 equals to ds. Okay, ds. And now how the parallel component of electric field and magnetic field behave across a medium. Now let's see that. Okay. So in order to see how the parallel component of electric field and magnetic field behave across a medium, now we are going to do the same thing. Okay. I have considered, as you can see, I have considered these two medium 1 and medium 2, and this parallelogram represents the interface. Okay. Now I have considered an Amperian loop. Okay, Amperian loop such that the upper half of the loop is in medium 1 and the lower half of the loop is in medium 2. Okay, this upper half is in medium 1 and this lower half is in medium 2. Okay, and since we are going to consider the parallel component of electric field, so what I have considered, I have considered the electric field in this direction. Okay, in the parallel direction. Okay. So now parallel to the surface. So let me write it down here. This is E parallel. Okay. This is E parallel. Now for perfect visualization, let me do this. Okay. Okay. So as you can see, this is what, this is medium 1 and this is what, medium 2, right? And this is the Amperian loop DL. This is what, this is the interface. Okay, this is the interface and this is the Amperian loop, and this is DL2, this is again DL sum, again this is some DL. Okay, now this is a rectangular Amperian loop. Okay, and the upper half of the upper half of this Amperian loop is in medium 1 and the second lower half of the Amperian loop is in medium 2. Okay, now from Maxwell's third equation what we have got. Okay, I hope this is clear, so let me erase this. Okay, let me paste it here. Okay, so from Maxwell's third equation what we got, that means from Faraday's law, B dot, sorry, this is E dot dl equals to minus del del T of phi b. Phi b means magnetic flux. Okay, I have taught you this in first class. Let's see where it is. Um, okay, as you can see here, this is a closed loop. Okay, closed circuit, and if the flux is changing in this closed circuit with respect to time, then the EMF induced can be written as minus d phi by dt, and this is equals to integration of E dot dl, as you can see here, right? So I am going to use this now. So here now I can write down phi b as what, minus d phi dt. Phi b can be written down as integration b dot ds, right? Sorry, b dot ds, right? So I am using this here. Okay, now similarly E dot dl can be separated into this four part. Okay, so what are those four parts? Okay, E dot dl, that means integration of electric field over this whole closed loop. Okay, so what I can write, okay, um, mm, okay, so for first this dl, okay, this side, what I can write, I can write it down as what, the integration sign will be removed since I am separating the whole four parts. Okay, so what, E, since this is parallel component and this is in medium 1, I can write dl. Okay, let's say this is dl1, and for this part, this side, what I can write, okay, there will be what, E1 also for the medium 1, for the upper half. For the upper half there will be E1. Okay, E1 parallel, let's say this is what, this is dl2. Okay, dl2 is in this direction. Okay, so this is dl2, dl2 is in this direction, this is dl3, and this is what, dl4, let's say. Okay, so now this will be one dl2 by half. Okay, half of dl2, since half of, only upper half of the Amperian loop is upside, okay, in the medium 1, and for the lower half, what I can write, E2 parallel dl2 by 2. Okay, plus for this region, what I can write, E2 parallel dot dl3. Okay, and similarly here E2 and E1 will be there, and this one will be okay. But now first let me tell you that E is in this direction and dl4 is in this direction. Okay, so angle between them is what, 90 degrees, so this value will be 0, right? So I am not writing this term again. Okay, this will be 0 again. Similarly for this term will be 0, this term will be 0, since this is dl2 is in what, dl2 is in this direction and E is in this direction, right? So angle between them is what, 90 degree. So again dot product will be 0, so both this term will be 0. So what I can write, E1 parallel dot dl1. Okay, but now E1 and dl1 is what, in this direction, and E is in also this direction, so angle between them is 0. So what I can write, I can write it as E1 parallel dl. Okay, 1. But for this term is 0, this term is 0, and for this term E2 is in this direction and dl3 is in this direction. Okay, so they are opposite to each other. So what I can write, there will be an minus sign. Okay, E2 parallel dl3. Okay, because as you can see, the dot product will contain one minus sign because these are opposite to each other and angle between them is 180 degree. Okay, so now what I can see, as you can see here, this is a rectangular loop, so dl1 and dl3 have equal length. So let's say dl1 equals to dl3 equals to, let's say, dl, right? So I can write it down as dl, right? As you can see here, E1 parallel dl minus E2 parallel dl. So this can be written as this. So here it is the explanation. Now as you can see here, what, here I have considered the magnetic flux, right? So here integration of B dot ds, right? So it is here. But now as you can see, if I squeeze this, okay, this is an Amperian loop, right? Okay, I hope you have understood this. So let me erase this, then I will be able to write it clearly. Okay, so let's say this is the medium 1, this is the medium 2, and this was the what, this was the interface. Okay, right, this was the interface. Now I have considered the Amperian loop like this, right? Okay, so this is dl, again this is dl. Okay, this as you can see, if if I squeeze the Ampérian loop such that there is no surface inside the inside the Ampérian loop. As you can see, I have squeezed the Ampérian loop. Now the surface inside the Ampérian loop is 0. So this value will be 0, right? Because ds will be what? 0. So integration of b dot ds will be 0. By considering this assumption, okay, so if I am going to squeeze the Ampérian loop such that it contain no surface inside it, then the integration value will be, this will be what? 0. So using this, I have got this E1 parallel dl minus E2 parallel dl equals to 0. So both these two term contain what? Both these two term contain dl. So dl will be cancelled and E1 parallel equals to E2 parallel. So the parallel component of electric field is continuous across the medium, okay, across the surface, okay. So as you can see, this is the parallel component of electric field, okay, behavior of parallel component. Now for parallel component of magnetic field, let us proceed further, okay. In order to find the behavior of parallel component of magnetic field, let us again consider a interface, okay. So there are two medium 1 and medium 2, and this parallelogram is indicating the interface, and we have considered the Ampérian loop such a way that the upper half of the Ampérian loop is in medium 1 and the lower half of the Ampérian loop is in medium 2, right? So as you can see, let me move it towards here, okay. So as you can see, this is dl, this is dl, again this is dl, okay. Okay, I am not writing it down, the perpendicular component, because the dot product will be always 0, right? As you can see. So since I am going to consider only the parallel component of magnetic field, so what I am considering? I am considering the magnetic field in this direction, okay. So this is what B or H, you can say anything, because both have same direction, okay, parallel direction. So this will be also H parallel, okay. So now using the Ampere circuital law, what I can write, B dot dl equals to mu naught I. Again, if I am going to move this mu naught towards left, what I will get? B by mu naught. So this is H, okay. H dot dl equals to I, right? And what is this I? This I is the current flowing at the center of this Amperian loop and perpendicular to it. As you can see, this will look like this. So if this is the Amperian loop, okay, this is not now the surface, this is the Amperian loop, and then this will be the current, okay. This is the Amperian loop and this is the current, okay. This is I, and I must be perpendicular to this Amperian loop, okay. So this is, and now as you can see, if there is some current, surface current, okay, and it has some direction, let's say ks, okay. So this ks is what? Ks is surface current direction. Let's say it is in this direction. This is ks, right? And in order to find the current which is perpendicular to this loop, okay, so what I am going to do, as you can see, this is n cap, and this n cap represents the direction which is perpendicular to the surface. So this is n cap, right? And this is what? This is ks. Let me write it down here, ks, okay. And this is what? This is dl. Now if I am going to take n cross dl, okay, n cap, this is n cap, right, cross dl, right? As we know, if we take the cross product of two vector, then what we get? We get another vector which is perpendicular to both these, okay, to the plane which contain both this vector, right? So if this is the Ampérian loop, okay, and this is the direction of the Ampérian, or this side of the Ampérian loop, this is the direction of this side of the Ampérian loop, okay, that means dl, and this was what? This was n cap, right? So what we will get, if we are going to take the cross product n cross dl, we will get a direction which is perpendicular to this loop, right? We will get such direction. Okay, this direction is perpendicular to this loop. Now the direction of current was what? This was arbitrary, let's say ks, right? It was ks and it was arbitrary and it was in the surface. Okay, so since it is surface current, it must be in the surface. Okay, so this is in the plane of the surface. Okay, so now if we are going to take the dot product of this direction, okay, with this ks, that means n cross dl, right? This is giving us what? This is giving us the direction which is perpendicular, direction which is perpendicular to the loop, right? Amperian loop. Okay, Amperian loop. Now again, ks was what? Ks was the surface current direction. Okay, so ks was the surface current direction. This was what? Surface current with direction. Okay, in some direction. Now if we are going to the dot product, then what we will get? We will get the amount of current in this direction. Okay, as you can see, when we take the dot product, then what we get? We get the uh, let's say, okay, let's say a and b are two factors, and if we take the dot product a and b, then what we get? We get the magnitude of a along the direction of b, or you can say magnitude of b along the direction of a. So what I can say, if we are going to take this dot product, then what we will get? We will get the uh, amount of current which is flowing in this direction, that means in the direction of n cross dl. Again, this is the current which is flowing perpendicular to this loop. Okay, through this loop. Okay, inside the loop. So this is the what? This is the value of I, because we need the amount of current which is flowing in the loop. Okay, and it is perpendicular to it. Okay, so I can be written as what? N cross dl dot what? ks, right? Again, this is the same argument as above. Okay, you can take the dot, we can separate this whole integral into the summation of this integration of these four sides. Okay, 1 2 3 4, and only these two term will survive, as you can see earlier. Now what I am going to do, I am going to now use some factor identity. Okay, as you can see, let me write it down. A cross b dot c. So this is equals to what? This is equals to C cross A dot B, right? That means minus of A cross C dot B. So consider this as A, this as B, and this as C. What I can write? This is equals to minus of what? A cross C, that means n cross ks dot dl. Again, all these three terms contains dl, so dl will be get cancelled, and what we will have? We will have h1 parallel minus h2 parallel equals to minus n cap cross ks, right? So the parallel component is not continuous for conducting interface, but continuous for dielectric. Why continuous for dielectric? Because only conducting interface, okay, only conducting interface contains surface current. Okay, this ks was what? Surface current, right? Surface current, right? ks, this term only ks term was what? Surface current, right? So only conducting interfaces contain what? Surface current. So the parallel component will be not continuous. But for dielectric does not contain free electrons. That means there are no free charges. Okay, so no free, that means no surface current. Okay, so this ks will be 0. So what we will be able to write? H1 parallel equals to, okay, sorry, let me write it down properly. H1 parallel minus H2 parallel equals to minus n cap cross dl. Sorry, it was ks, right? But now ks equals to 0 for dielectric, since they doesn't contain any surface current, so this will be equals to 0. So H1 parallel minus H2 parallel equals to 0. So what I can write? H1 parallel equals to H2 parallel. So this is for dielectric only, okay, dielectric surface, not for conducting interface, okay. So these are the four equation which describe the behavior of electric and magnetic field across a boundary. So what are those? One is this one, right? And second one is this one. This is the perpendicular component of the magnetic field. The above was perpendicular component of electric field, and this one parallel component of electric field, and this was what? This was parallel component of magnetic field, okay. So on the basis of all these four equations, what I am going to do, I am going to find the condition of reflection and refraction, okay, and we will do that in the next class, okay. So this is the end of today's class. Thank you all.